In section 7.6, we're looking at radical equations and problem solving. In this section, we present techniques to solve equations containing radical expressions such as the square root of 2x minus 3 equals 9. We will use the power rule to help us solve these radical equations. The power rule says that if both sides of an equation are raised to the same power, all solutions of the original equation are among the solutions of the new equation. Now, this property does not say that raising both sides of an equation to a power yields an equivalent equation. So a solution of the new equation may or may not be a solution of the original equation. For example, negative 2 squared is equal to 2 squared, but negative 2 doesn't equal 2. So each solution of the new equation must be checked to make sure it is a solution of the original equation. Recall that a proposed solution that is not a solution of the original equation is called an extraneous solution. So you want to just make sure that you are really checking the answers that you get when you start raising the sides of an equation to a power. So let's go ahead and solve the square root of 2x minus 3 equals 9. The first thing you want to do is make sure that the square root, or whatever the root is by itself. So in this case, it already is. And so to undo a square root, we use the index and we're going to raise both sides to that power. So to undo a square root, we are going to square both sides of the equation. What ends up happening is that the square root and the square cancel, and we're just left with the piece that's underneath. So in this case, just 2x minus 3 is equal to 9 squared, which is 81. Now from here, we're just going to solve as normal. Let's go ahead and add 3 to both sides of our equation. So we end up getting 2x is equal to 84. And then the last step is to divide both sides by 2. And we end up getting x equals 42. Now remember, you need to check this in the original equation. So let's go back to the original. We're going to check x equals 42. So we have the square root of 2 times 42 minus 3, and this should give me 9. Well, 2 times 42 is 84. And 84 minus 3 is 81. And the square root of 81 is definitely 9, so this checks out. And that means that we can keep x equals 42 as our solution. So like I said before, you first have to isolate the radical by itself on one side of the equation. So let's go ahead and look at example number 2. We have the square root of negative 10x minus 1 plus 3x equals 0. We want to make sure the radical is by itself first, so we're going to subtract 3x from both sides. So we end up getting the square root of negative 10x minus 1 equals negative 3x. Now that it's by itself, we're going to square both sides to get rid of the square root. So on the left, the square root and the square cancel, and we're just left with negative 10x minus 1 equals 9x squared. Now from here, we have a quadratic, so we need to set this equal to 0 to solve it. So we're going to add 10x, and we're going to add 1 to both sides. So it cancels on the left, and we get 0 equals 9x squared plus 10x plus 1. Now from here, we're going to factor the right-hand side. When I factor, I end up getting 9x plus 1 and x plus 1. We're going to set each of these equal to 0 and then solve. So in the first one, we're going to subtract 1 from both sides. And we get that 9x equals negative 1. And then we're going to divide by 9 on both sides. And so we end up getting x equals negative 1/9. And in the other equation, we're just going to subtract 1 from both sides. And we get that x equals negative 1. Now you need to check both of these solutions in the original equation. When you do check them, they both turn out to give you true statements, so we can keep both of these solutions. So to solve a radical equation, the first thing you want to do is isolate one radical on one side of the equation. You'll raise each side of the equation to a power equal to the index of the radical and simplify. If the equation still contains a radical term, you're going to repeat steps 1 and 2. If not, solve the equation, and then check all proposed solutions in the original equation. So let's go ahead and try another one. We have the cube root of x plus 1 plus 5 equals 3. The first thing we need to do is make sure the radical is by itself. So I am going to subtract 5 from both sides. And so it cancels on the left. We have the cube root of x plus 1 equals negative 2. Now to undo the cube root, we are going to cube both sides. And so on the left, the cube root and the cube cancel. We're just left with x plus 1. And on the right, negative 2 cubed is going to give me negative 8. Now we're almost done solving for x. We just need to subtract 1 from both sides. And we end up getting that x is equal to negative 9. Again, you want to make sure that you check your solution in the original equation, and this one does check out, so we can keep it as our solution. For example number 4, our square root is already isolated on one side. So all we have to do is get rid of it by squaring both sides. So on the left, we're just going to be left with 4 minus x. And on the right, I'm going to write this twice so that I can FOIL it. So we end up getting 4 minus x equals x squared minus 2x plus 4. We have our like terms in the middle. So we end up having 4 minus x equals x squared minus 4x plus 4. Now this is a quadratic, which means we need to set this equal to 0 so we can solve it. So we're going to subtract 4 and add x to both sides. And so the 4's end up canceling, and so do the x's. And on the right-hand side, our 4's end up canceling as well. So we have 0 equals x squared minus 3x. Now from here, we're looking for our greatest common factor that we can pull out. And we could pull out an x from both pieces. And we're left with x minus 3. So setting these both equal to 0, we get x equals 0, or we get x minus 3 equals 0. The first one's already solved for, and the second one we're just going to add 3 to both sides. And so it ends up canceling. And then we get x is equal to 3. Again, you always want to make sure that you check your solutions. When I plug in x equals 0, I end up getting a false statement. So we're not going to use 0 as a solution, but 3 did give me a true statement. And so the only solution that I have is x equals 3. And let's try one with 2 radicals involved. The first thing that we want to do is we are going to isolate one of the radicals on one side. It does not matter which one it is, as long as one of them is isolated. So we have the square root of 2x plus 5 plus the square root of 2x equals 3. I'm going to isolate the square root of 2x plus 5, so I'm going to subtract the square root of 2x from both sides. So we have the square root of 2x plus 5 equals 3 minus the square root of 2x. So to undo our square root, on the left-hand side, we are going to square both sides. And so on the left, we end up with just 2x plus 5. And on the right, I'm going to write this twice so that I can FOIL it. So on the right, we end up with 9 minus 3 times the square root of 2x minus 3 times the square root of 2x plus the square root of 4x squared. And so we actually end up getting a perfect square with our 4x squared. And we have like terms in the middle. So we have 2x plus 5 equals 9 minus 6 times the square root of 2x plus 2x. But I still have a radical that's involved. And so I need to isolate the radical so that I can repeat the process over again. So we need to make sure that that square root of 2x is as isolated as possible. So I'm going to subtract 9 from both sides, and I'm going to subtract 2x from both sides. So on the right, it cancels, and on the left, the 2x ends up canceling. And we end up getting -4 equals -6 times the square root of 2x. And from here, we can actually just go ahead and square both sides. Now when I square, I end up getting 16 equals, make sure you square both the -6 and the square root. So the square of -6 is 36, and the square and square root cancel, we're just left with 2x. And so we end up getting 16 equals 72x. And the last thing is to divide both sides by 72. And so we get that x is equal to 2/9. Again, you always want to make sure that you check your solution. And since this does check out in the original equation, x equals 2/9 is the solution to our equation. Recall that the Pythagorean theorem states that in a right triangle, the length of the hypotenuse squared equals the sum of the length of each of the legs squared. Or a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. We're going to use this to solve example number 6. A 50-foot supporting wire is to be attached to a 75-foot antenna. Because of the surrounding buildings, sidewalks, and roadways, the wire must be anchored exactly 20 feet from the base of the antenna. How high from the base of the antenna is the wire attached? So what exactly are we looking for here? We are really looking for x, which is this line. We don't know what it is. So we can utilize the Pythagorean theorem here. We have x squared plus 20 squared equals 50 squared. We'll simplify. We have x squared plus 400 equals 2,500. Subtracting 400 from both sides. We get that x squared is equal to 2,100. And so taking the square root of both sides, I have plus or minus the square root of 2,100. And we only care about the plus part because we're talking about length. So when I simplify this, I end up getting 10 times the square root of 21. Or as a decimal approximation, this is about 45.8 feet. Local regulations require that a supporting wire be attached at a height no less than 3/5 of the total height of the antenna. From Part A, have local regulations been met? Well, the total height of the antenna is 75 feet. So let's figure out what 3/5 of 75 is. Now remember, we multiply across the top and bottom. So we end up getting 225 over 5, which is 45 feet. So have local regulations been met? Because we had our original answer be 45.8 feet, and the regulation is 45 feet, we have met the regulations barely, but we have met them. So yes, regulations have been met.